Alright gang, here we go. This is for Physics Unit 9, Part 3, Video 1. We're going to split this guy into two videos, one about electrical potential, and then the next one will be about capacitance. So this will be the first half of Part 3. Alright, so before we jump into electrical potential, let's just go back and review gravitational potential energy real quick. So imagine that you're a dude, right, and you're, or a lady, doesn't matter. You can imagine how, whatever gender you want to be, no judging. Okay, and you're here on the ground, okay, and you're at a height of 0. Okay, and so we've defined before that the potential energy due to gravity is equal to mass times gravity times the height that you're at. So that however much mass you have times the gravity of whatever planetoid you happen to be on times the height off whatever flat surface you've defined. All right, and so here your potential energy equals 0. Okay, and then if you take this, and you like climb up a ladder, and then now you're up on top of a ladder, and let's say you're 5 meters up now. And so you're up there, you're 5 meters. That means your height is now 5. All right, so now you're at 5 mgh. Or 5 mg, sorry, 5 mg. And so this value here is a representation of how much potential energy you have. Now, what is that potential energy? Now, when we talked about potential energy, it was just essentially like, can you fall, right? And so, yeah, if you're on the ground, no, you cannot fall. So there's no potential energy in your fallingness, right? You could just kind of flop down exactly where you are. If you're 5 meters up in the air, then yeah, there's a chance that you could fall. And when you fall, this is how much energy that you'd build up on your way down. So this is the amount of potential energy gravitationally that you've stored in your experience of being above the ground a certain amount, right? And so so take that idea real quick, and we're going to apply that to electric fields, because in the past couple of videos we've talked all about electric fields and this idea that you can take a particle, right, and we'll say that that's a positive particle, and coming from this positive particle are these electrical fields, right? And we define these as like, well, where would a positive charge move? So if you took a negative charge here, right, and we'll say that guy's negative, you know that these two would be attracted to one another because one's positive, one's negative. So if you take these two charges and say you've got small enough fingers that you can hold these two charges away from one another, and you can almost think of them like magnets, and you've got one positive and one negative, and you're holding them far apart from one another, and but because they're oppositely charged, there's a force, that electrical force is trying to bring them together. Now if you grab them and you try to keep them apart from one another, you can imagine just like almost like you were holding two very strong magnets. You're holding magnets apart from one another. They're trying to pull each other, right? And so it's the same idea. If you're holding something above the ground, you can feel gravity pulling down on it, right? That you're fighting against that gravitational force. So if you have two charges and you pull them apart from one another, and you keep them apart from one another, it takes a certain amount of force to keep them there, then you're fighting against the electrical energy, right, as opposed to the gravitational energy. And so we can quantify this potential energy that charges have when they're in an electric field. It's essentially what we're doing. So we call that electrical potential energy. So it's the same idea as gravitational potential energy, but it can be a little bit trippy to think about for a couple of reasons. Number one, gravity is nice because we automatically think of gravity as moving up and down, right? And so that makes life a lot easier to think about. And then number two, gravity only pulls in one direction, right? So if you're above the ground, you automatically have some gravitational potential energy. Whereas electrical potential energy, in the example we just talked about here, we talked about this charge was negatively charged versus a positive charge. Now, it would be a totally different, our potential energy would be a different sign. It would be in a different direction if we had both of them were positive charges, as opposed to them being oppositely charged, so they wouldn't necessarily act in the same way. All right, and so here in this example here, we've got our electric field, right? And so this is our big E. Our electric field is pointing this direction, and here's our test charge A. And if we move it from A to B, okay, because remember the electric field lines show us where a test charge would move. That's the path a test charge would take in this electric field. And so this test charge would move to the right. Now, as it moves to the right, it would lose potential energy, right? Because this electric field is forcing it to go in that direction. Okay, and so we would have this A charge here would be going to the right, and so it's the same idea. If you kind of turn your head like this and you look at it, you can imagine that it's actually just falling. So it's losing electrical potential energy as it's going. All right, and so as it's moving with the electric field. It's actually losing potential energy. Okay, so it's very, very similar to a falling object losing potential energy, and because of that, we can kind of use this formula here. Our potential energy electric equals work done, and we talked about this at length several units ago now, and work is equal to force times distance, and force is equal to force of an electric field is just equal to the charge times that electric field, and then there's your distance. So negative QED is the potential energy due to electric field. Okay, now the trippy thing here, and the reason we have this negative sign here is because you could imagine that if you had a negative charge here and it went this direction, then it would be actually fighting the electric field. Remember, because the electric field points in the direction that the positive charge would go, a positive stress charge. So the electric field, if you put in a negative charge in there, it would want to go opposite of that. So if you would have to force it to go in that same path that the positive charge is taking. And so that is really what would give you. So if instead of our A being a positive charge, it was a negative charge, it's actually going the wrong. It would be going the wrong way, and its potential energy would actually be going up. Pretty wild, right? And that's really the crux of, well, why is electrical potential energy so much different than gravitational potential energy? Is it purely because you got to friggin' think about whether or not you got positive or negative charges, and then they can move opposite of one another, and then it's trippy. It really is. Okay, so here's our formula. Okay, potential energy due to electric field, or electrical potential energy, is equal to negative charge times the electric field strength times the displacement from the reference point. And again, remember our potential energy, okay, due to gravity is equal to m times g times h. H and d, I mean, they're pretty obviously the exact same thing, right? Your d here is your distance from your reference point, and your h here is your height above the reference point. And we can use height instead of d because gravity only pulls down, and so we're just measuring the distance up. So that makes life easy. E here is the strength of the electric field, and G is our strength of our gravitational field. Okay, and then Q here is the mass, and essentially this is saying, well, how much is my field strength going to affect this individual thing that we're talking about? Gravity is, if the more massive you are, the more gravity is going to be pulling down on you, so on and so forth, because it's all due to the fact that we've got Coulomb's law versus Newton's law of gravitation. G is equal to m1 m2 over r squared versus Coulomb's law, Fe equals Coulomb's constant times Q1 Q2 over r squared, right? And so that's the reason they're so dang similar to each other, is because these forces act almost exactly the same. Okay, so here's your two big caveats. Maybe if you get confused trying to think about all this stuff, it's totally understandable. It takes a fair amount of work unless you're just kind of gifted in this regard, to kind of think through what's going on. All right, so you could just kind of memorize these. Your potential electric field is positive if under these two cases. All right, and then the other two cases would be negative. So it's positive if your charge is negative and it moves with the field. Okay, and then it's positive if your charge is positive and moves against the field. All right, so negative with, positive against. Okay, and then the two cases where you'd be negative is if your negative moves against the field and your positive moves with the field. All right. So practice problem here, you've got a uniform electric field strength of this, so this is your E value, that's nice, 1 times 10 to the 6th. Exists between a cloud at a height of 1.5 kilometers and the ground. A lightning bolt transfers 25 coulombs of charge to the ground. What is the change in potential energy for this lightning bolt? Well, our potential energy due to the electric field is equal to negative Q times our electric field times the displacement. All right, so it'd be negative Q, and our Q was 25. All right, there's our charge. Okay, and our electric field is 1 times 10 to the 6th. And then we're 1.5 kilometers to the ground. We got to convert that to meters, so it'd be 1,500 meters. All right, and that's about it. Pretty easy. Negative 25 times 1 e to the 6th times 1,500. And we get negative 3.75 times 10 to the 10th. And then because it's energy, it's in joules. All right. gravitational potential difference. So let's take a step back, talk about gravity. This is review from before. So suppose a mass of 2 kilograms is moved from point A straight up to point B. That's a distance of 3 meters. All right. So you've got some height here, and you've got, so this would be our A, this would be our B, and they're 3 meters apart. So 3 meters from there to there. Find the potential energy change for gravity, gravitational potential energy change for the mass. Repeat, and so you've got one object that's 2 kilograms, so a 2.0, and then another object that's 5. So here's our 5. All right, 5 kilogram object, and we're going to move it from A to B. All right, so the potential energy due to gravity for the, we'll say this 2.0 kilogram object, well, this would just be mgh, which would, so our mass is 2 times our gravity, 9.81, times our height is, and it's moved up 3 meters, so times 3. So it'd be 2 times 9.81 times 3. All right, we get how many sig figs? We want 3 sig figs, so 58.9. And then this is energy, so it'd be joules, and then potential energy due to gravity for the other guy. So this is our 5. That would just be 5 times 9.81 times 3. So 5 times 9.81 times, times 3, we get 147 joules. All right, so we got the same answers. Good for us. Rocking and rolling. Okay, and it says, what is the potential energy change per kilogram for each object? So essentially all we need to do is take our potential energy and divide it by the mass. So so for the 2 kilogram, okay, how do I want to notate this? The change in potential energy for gravity for the 2 kilogram is equal to, it'd be 58.9 divided by 2.00. All right, so 58.9 divided by 2, we get 29.5. And then for the other one, our change in potential energy due to gravity for the 5 kilogram would be equal to 147 divided by 5. We get 29.4. All right, so notice that, I mean, just rounding errors is what's affecting us here, but essentially these guys are the exact same value, okay? Your change in gravitational potential energy does not depend on the mass, or per kilogram does not depend on the mass. It only depends on the field strength and how far away you've moved it. Okay, and so this is the same idea for an electrical potential energy. It only matters how strong that field is and how far away from it is. And so we think about electrical potential energy as well, how strong is the thing that's causing the field, and then how far away is it. All right, and so really we don't care so much about that total electrical potential energy. We care about the potential difference. And this is a lot more of a helpful idea to think about, especially when you're talking about circuits that we're getting to soon. All right, so potential difference is known as the change in electrical potential energy per coulomb. Okay, and so essentially all we're doing is we're taking our, that's this straight line or spare line, we're taking our change in potential energy to the electric field divided by our charge. Okay, and so it'd be final minus initial, so this would be equal to, and you can think about it this way, but this is the hard way, potential energy due to the electric field final minus potential energy initial over RQ, right? And you can calculate it that way if you have all the necessary information. All right, and so what's nice about this is that the charges will cancel out, right? Because this was Q, right? This is QGH or QED, and QED over Q, so it just becomes the difference in the electric field, and the electric fields are the same, so it really just depends on the strength of the electric field and then the initial and final positions. Okay, and so the amount of charge doesn't matter at all. All right, and so we get this new idea here called the potential difference. Okay, and this potential difference, the SI units is joules per coulomb, but that's, J per C, and so we use this guy here. So if you hear about like a 12-volt battery, essentially what we're talking about is it's 12 joules per coulomb of charge. Okay, and so and that's that. Okay. So your potential difference in a uniform electric field, this is what your formula comes down to. It just has to do with the electric field times the displacement. Magnitude of the electric field times the displacement. Super easy. Okay. And then this part gets a little bit more confusing. Okay, so this is when you have a charge that's close to the point charge, and then imagining that charge when it's very, very far away from that point charge. And it simplifies a lot of things down, okay? And this is the big formula that we really care about here, okay? The last one is important, but this one makes our life way easier because of the way things cancel, and we could derive it if we wanted to. It's not too terribly difficult. But essentially what we're saying is the potential difference really boils down to Coulomb's constant times the value of that point charge. So this is not your test charge or what's moving. This is the point charge divided by the distance. Notice that is not distance squared. Okay, so this is a little different than what you're used to. All right, because up to now we've always cared about the square of the distance. Here we only care about just the value or that distance. Okay. Okay, and this is comparing 2 point charges that are one point charge that's one charge that's close to your point charge and one that's infinitely far away from your point charge. So you can assume that the one infinitely far away has a potential energy of 0. Okay, just because it's too far away. Just like imagine if you were infinitely far away from the Earth, the gravity field of the Earth affecting you would be essentially 0. All right. Now, one thing you should keep track of here, okay, is that the potential energies here are scalars. Okay, so they're not vectors. Okay, and so because of this, we can use that law of superposition, position that we talked about. When we talked about electric forces. All right, and so we're going to let the textbook help us out here. I guess I need to go back to just a regular old arrow to get it to let me click this. All right, and so here we go. Let's listen.
According to the superposition principle, the electric potential at a point is the algebraic sum of all the individual potentials existing at that point. The strength of the charges, their polarity, and their distances from the point in the middle completely determine the electric potential at that point. This is because, in contrast to a vector quantity, electric potential is a scalar quantity and has no direction associated with it.
So really all we have to do, the setup, this is exactly what we've talked about, but because Kc is the same in all of them, we can pull them out here. And so we've got just the Q1 over R1 plus Q2 over R2. So if we want to figure out what the potential difference is at this point, we just need to figure out what the potential, we can just take all these guys and then add them up, and it's just a scalar addition.
Calculating the electric potential at a particular point is simply a matter of finding a scalar sum.
Okay, and so we've just taken these values here, and we've taken these values here and just added them up, plugged in their values, the charges, and how far away they are, and then so you can figure out the potential difference at that point. Pretty easy. All right. So last little bit here. So how does this apply to real world stuff? Well, this has huge implication for energy, circuits, so on and so forth. Batteries, though, you hear about 12-volt batteries, 1.5-volt batteries, 9-volt batteries, all sorts of different batteries. And essentially what you're doing is just measuring the potential difference between the two terminals of your battery. So like a 9-volt battery, forgot my pen was gone. So you're like 9-volt battery here, right? A big old square dude, right? This would be 9 volt, okay? It's got two terminals, one that's kind of like big and flat, kind of like a circle, like this, all right, like that, and then it's got one that's kind of like this. And essentially, like if you were going to take a voltmeter and, measure the difference in energy between these two, the potential difference, you would find 9 volts, okay? And so that's essentially what we're doing, is we're using chemical energy, okay, in order to separate these two things, all right? And so inside a battery are just different chemicals dissolved in different substances, and so that's like, for example, like your battery in your car uses sulfuric acid. So that's one of the reasons why if you never want to like mess around with the fluids in your batteries, okay, so on and so forth. The ones like AA, AAA, all these guys are alkaline batteries, so they use bases instead of acids. So they're slightly more safe, but at the same time, you still don't go taking a hammer to a battery, because the chemicals in there are still pretty gross. They're pretty nasty. All right. So in a 1.5 volt battery, the electrons are held at a higher potential energy via chemical energy, and they're moving from the positive to the negative terminal. Okay, and so they gain 1.5 joules of energy per coulomb charge, and that's essentially what this means, right? Because this is in joules per coulomb. All right. So when you connect your flashlight to a battery, the electrons are moving from the battery to the bulb, and as they do that, they lose 1.5 joules of energy per coulomb of charge. Okay. And so this is potential energy. Now this stuff might seem pretty easy when I'm explaining it to you, but I promise you, when you sit down and actually start doing practice problems, this can actually be pretty confusing and trying to decide which formula to use, because these are completely new terms. Like when we talked about gravitational potential energy, you've watched things fall since you were born, right? Like probably in the delivery room, one of the nurses dropped something, and your poor little baby eyes saw that thing fall to the ground, and you started to understand how gravity works. Now, the electrons and their potential energy, you have no idea, right? We don't see electrons. We can't see them with our eyes. And so this is all kind of like this mumbo jumbo magic. It takes practice. Okay, so don't neglect doing the practice problems, because if you don't do the practice problems, you're not going to be able to do the problems. And so don't be afraid to ask questions, and don't be afraid to not know. All right, you'll be all right. Okay, so do your practice problems. Let me know if you have any questions, and I'll see you on the flip side.